Hey there, space cadets! Ever feel like time flies when you're having fun? Well, it actually does, at least relative to someone else. It's called time dilation, and it's one of the universe's coolest tricks. Einstein blew our minds when he said time isn't constant. It's more like a river, speeding up and slowing down depending on where you are and how fast you're moving. Imagine this: two identical clocks, one sitting still, the other on a rocket ship, zooming through space. Here's the kicker: time on the speeding spaceship actually slows down compared to the clock on Earth. The faster the spaceship goes, the slower time ticks for the astronauts on board. Crazy, right? Now don't go planning any time-traveling vacations just yet. The differences are super tiny at everyday speeds. But at super high speeds, like those close to the speed of light, time dilation becomes really noticeable. Think interstellar travel. To wrap your head around this mind-bending concept, let's picture a simple clock, a light clock. It's just two mirrors with a beam of light bouncing between them. Tick-tock, tick-tock. Each bounce is like a tick of the clock. Now imagine this light clock is on our speeding spaceship. From the perspective of someone on Earth, the light beam isn't just going up and down, it's also moving horizontally with the spaceship. This creates a longer diagonal path for the light to travel. Since the speed of light is constant, and the light has to travel farther on the moving clock, time itself must slow down on the spaceship. The faster the spaceship, the longer the light's path, and the slower time moves for the astronauts. But how much slower does time actually get? Well, there's a formula for that. It's called the time dilation equation, and it looks a little something like this: dt equals sine dt divided by the square root of 1 minus v squared over c squared, where dt is the time interval measured by the observer in motion relative to the event, dt is the time interval measured by the observer at rest relative to the event, v is the velocity of the moving observer, and c is the speed of light. Don't let the symbol scare you. It basically says the faster you move, v, the bigger the difference in time between you and someone standing still. But remember that c is the speed of light, which is a seriously big number, so you need to be moving crazy fast to see a significant difference in time. So, time dilation is real, but does it actually matter in our lives? You bet it does. In fact, we see its effects all the time, literally. Take GPS satellites for example. They're zipping around Earth super fast, which means their clocks tick a tiny bit slower than clocks on the ground. Now this might not seem like a big deal, but even a tiny difference in time can throw off GPS coordinates by miles. That's why engineers have to adjust for time dilation to make sure your GPS can tell you exactly where you are and how to get to that awesome new restaurant. And what about astronauts on the International Space Station? They're orbiting Earth at a pretty good clip too, which means they experience time dilation too, albeit a tiny amount. It's like they're taking mini trips into the future. Time dilation might seem like science fiction, but it's a fundamental part of our universe. It affects everything from satellites to astronauts and even our understanding of the cosmos. So next time you're running late, just tell everyone you were experiencing some time dilation. They might think you're a genius, or maybe just a little bit spacey.